Okay, let's do another example. A researcher wishes to test the hypothesis that increased illumination increases employee productivity. Two groups are randomly selected from employees at Hawthorne Electric Company. Each group is given a task and the amount of time in hours to complete that task is recorded. Group A works with normal lighting conditions while Group B works with a 50% lighting increase. Their scores are as follows in Group A and Group B. Okay, so I have gone ahead and written down all the formulas that we need to solve this independent t, and I've gone ahead and looked through those formulas and seen what pieces we need to plug into here. So since we have our data here, let's go ahead and get started. So how many people do we have in each group? So in Group A, we've got 1, 2, 3, 4, 5, 6, 7. So that's our N value for Group 1 or Group A. And then for Group B, 1, 2, 3, 4, 5, 6, and 7. Okay, so we can go ahead and figure out our degrees of freedom too, since we have N1 plus N2. So N1 is 7 plus our N2 value of 7 minus 2. So 7 plus 7 is 14 minus 2 equals 12. So 12 is our degrees of freedom. Next, let's go ahead and find our mean. So in order to find our mean, we need to add up the scores from each group and then divide it by how many we have in each group. So when we add up all of these scores, that is going to give us 35.6. Okay, so our formula for mean is the sum of the scores divided by how many you have in your sample. So we have 35.6 divided by our N value of 7. So when we divide that out, that is going to give us 5.09. So for Group 1, we have a mean of 5.09. Okay, so let's go ahead and do for Group 2 or Group B. So once again, we add all of these together. That is going to give us 27.1. So we're going to do the same thing. So we have 27.1 as our sum of raw scores here, divided by our N value of 7. And that is going to give us 3.87. So for Group 2, we have a mean of 3.87. Okay, so for the sum of squares, which is this here, we take our raw scores and we square them, and then we are going to add all of these up. So I went ahead and wrote down what each of the values was squared. So now all that we have to do is add them up for each group. So here, we'll just go ahead and label this here. There we go. Okay, so for Group A, when we add all of the squared scores together, we get 86.88. Okay, so we have 186.88. Okay, and then we go ahead and do the same thing over here for Group 2. So that is going to give us 107.27. We're just adding all of these numbers up here. So 107.27. Next, let's go ahead and find our standard error of the mean. Okay, so we have got our formula for standard error of the mean here, so we're just going to plug these values in. So we have to do that twice because we have two different groups. So let's start with Group 1. So our standard error of the mean for Group 1, we are going to have our sum of squares valued of 186.88. That is going to be divided by our N value of 7, minus our mean for Group 1 of 5.09. That's going to be squared over N value of 7 minus 1. And then all of that is square root. Okay, so when we divide 186.88 by 7, we get 26.70 minus 5.09 squared is going to give us 25.91. 7 minus 1 is 6. Okay, so 26.70 minus 25.91 is going to give us 0.79, and then that's going to be over 6. Then we divide that out. That is going to give us 0.13. Then we find for the square root of that, and that is going to give us 0.36. Okay, so our standard error of the mean for group 1 is 0.36. Okay, so now we're going to do the exact same thing for group 2. So our sum of squares is 107.27 over in value of 7 minus the mean of 3.87 squared over in value of 7 minus 1. Okay, so 107.27 divided by 7 is 15.32 minus 3.87 squared is 14.98. 7 minus 1 is 6. Okay, so we're going to go ahead and subtract these two numbers. When we do that, we get 0.34 over a value of 6. Divide that out. That will give you 0.06. And then solve for your square root, and you have 0.24. So our standard error of the mean for group 2 is 0.24. Next, let's find our standard error of the difference and our t-value. So since we went ahead and found our standard error of the mean, we're just going to plug that into this formula here. So our standard error of the mean for group 1 is 0.36. We're going to square that, plus standard error of the mean for group 2 is 0.24, and we're going to square that as well. Okay, so when we square 0.36, that is going to give us 0.13. We're going to add that to 0.24 squared, which is 0.06. Okay, so we're going to add 0.13 to 0.06. That is going to give us 0.19. Then we're going to solve for our square root. That is going to give us 0.44 for our standard error of the difference. So 0.44. Okay, and now that we have that, we can go ahead and solve for our t-value. So we're just going to plug these values into this formula here. So our mean for group 1 is 5.09 minus our mean for group 2 of 3.87 over our standard error of the difference, which was 0.44. Okay, so 5.09 minus 3.87 is going to give us 1.22 divided by 0.44. Okay, and then we're just going to go ahead and divide that out, and that is going to give us 2.77. So our final t-value is going to be 2.77. Okay, so before we figure out if we are going to accept or reject HO, let's go ahead and take another look at our word problem and see if we are dealing with a one-tail or a two-tail independent T. So a researcher wishes to test a hypothesis that increased illumination will increase employee productivity. Two groups are randomly selected from employees at Hawthorne Electric Company. Each group is given a task, and the amount of time in hours to complete that task is recorded. Group A works with normal lighting conditions, while Group B works with a 50% lighting increase. Okay, so the problem, while it does not have any key words such as better, worse, anything like that to indicate a direction, it is making a prediction. It is saying that increased illumination is going to increase employee productivity. So that is saying that one group is going to do better than another group. So since we have that prediction, that means that we are dealing with a one-tail independent t-test. Okay, so now that we know that, let's go ahead and put in our degrees of freedom so we can look up our critical values. Okay, so we calculated a degrees of freedom of 12. So that goes in here. Okay, so now we're going to pull up our critical values of T table, and we are going to use this one down here on the bottom because that is for a one tail. So for our 0.05 level, let's see, we go down to 12. So for our 0.05, we have 1.784 2, and for the 0.01, we have 2.681. Okay, now let's go ahead and test our t value against those critical values. So is 2.77 greater than 1.782? Yes, it is. Is 2.77 greater than 2.681? Yes. That means that we reject HO, and because we rejected at the 0.01 value, we write it as P less than 0.01. Lastly, if you wanted to put your findings into a sentence form, here is a little template that I use for independent T's. So you start by saying there is a significant difference. Now, if you did not find a significant difference, obviously you would put there is not a significant difference. But for this problem, we did find a significant difference. So there is a significant difference in, and then in this spot here, you write your dependent variable. So our dependent variable for this problem was the amount of time taken to complete a task. So the amount of time taken to complete a task. Okay, between, and then you put your first group and your second group. Now group 1 had the normal lighting, so between the group working with normal lighting, and then our second group was the group working with increased lighting. Okay, and then you put your findings here. So that is suggesting that increased lighting can increase productivity. Okay, so your whole entire finding is going to say there is a significant difference in the amount of time taken to complete a task between the group working with normal lighting and the group working with increased lighting, suggesting that increased lighting can increase productivity. So congratulations, you guys just did independent T. Good job, guys.